Okay, section 4.3, complements and conditional probability. We're going to skip Bayes' theorem. That could be a whole semester class, to be honest. Okay, we're going to do the at least one problems first because these involve the complement. We kind of did this in the last section with the Airbus and the hydraulic systems. We actually used the complement to solve that problem. Now, at least one. If I said at least one student in the class is 20 years old, that means I have one or more. The complement to that would be no students being 20 years old. So at least one 20-year-old. There could be 7 of you. But if I want to have the complement of at least one, that means no 20-year-olds. So the way we're going to do this is we're going to relate the probability of an event and its complement. So I'm going to do a probability of at least one is equal to 1. I'm going to subtract the probability of none, which is the complement. That's the event. That's the complement. And then here, we're going to use the and in multiplication. Which will be evident when I do an example. This is what we just did. And this is how I start every one of these problems. Okay, I don't like the example in the book. You can read that one. I'm going to do problem 10. Because I think you can imagine doing this. You've got 10 multiple choice questions, each with 5 answers. And you're at the end of the exam, you're just going to guess. What's the probability of getting at least one correct? So let's do that and then we'll come back to the second question. So the probability of at least one equals 1 subtract the probability of none correct. Well, what's the probability of getting a question right? Well, if you guess and there's 5 possible answers, getting it correct is 1 out of 5. So the probability of being wrong is the complement of that is 4 out of 5. Now, how many are you guessing on? You're guessing on the first and the second and the third, all the way up to the 10th. So the probability of you being wrong on the first is 4 out of 5. Also the second and the third, all the way up to the 10th. And because it's and, we're going to multiply all of these. Well, this is where exponents come in. We're doing 4/5 to the 10th power because we multiplied it 10 times. You probably converted to a decimal, so we've got this. This is what's going to go in there. That's the probability that we get none of them correct. So it becomes a calculator problem now. 1 subtract, let me write what we're doing. Probability of at least one correct is now equal to 1 minus none correct is 1 subtract this 0.8 raised to the 10th. You may need the y to the x button on your calculator. Raise 0.8 to the 10th power. This, so we are now at equals 1 subtract. I'll do that. This is 0.107. Subtract it from 1. 0.893. So that's the probability of guessing on 10 and getting at least one correct. So that's one or more. So that's pretty high probability. So if you must get at least one correct before continuing, I think there's a good chance. Probability was 0.893. So that's the structure of these problems. You end up multiplying, so you use the exponent button quite a bit. Notice where that 10 came from? You guessed on 10 multiple choice questions. Let's do this quickly. Let's just change a number. This is all the same. Let's change it to 3. So we want the probability of getting a question correct. At least one. Should have just erased everything. One, subtract the probability of none. The only thing that changes here, it's still 4/5 chance or probability of 0.8 that we get it wrong, but now we're only guessing on 3 of them. This is 0.512. Notice it's a lot larger because we're multiplying a small number less times. Here, there's not such a good chance, and we may not be able to continue. Okay, that's using the complement. Conditional. We're doing probabilities based on the fact that some other event has already occurred. So this says we're finding the probability of B given that, I see this as given that, that's that symbol, event A has already occurred. We did this like dealing 2 cards. What's the probability of 2 aces? Well, the probability of the first ace is 4 times 52, but now there's a condition on the second one. There's only 3 aces left in the deck, and there's only 51 cards left in the deck. So the fact that A occurred affected the probability of event B. But we're going to do this differently with tables. We're going to do the intuitive approach. because formulas are confusing, and we're going to do tabular data here. So I'm going to do this problem, then I'm going to do one from the book. So there's 555 test subjects. So here is the row that subject uses drugs. Here does not use drugs. The column is they have a positive test result, negative test result. So let's see. The probability that a subject has a positive test result, given that, that's the huge thing here, the subject actually uses drugs. So let's explore what that does to our table. So the subject actually uses drugs. That's this row. I just look at this data. So my total here is 50 subjects. Positive test result is 45. But there's only 50 because I'm adding all the tests just in that row. This is 0.90. So my condition is the given statement, and I focus on a row or a column. So let's do one with a column. Find the probability that the subject actually uses drugs, given that he or she had a positive test result. Now I'm focusing on the column. So here, uses drugs, that's 45. But now I have 70 total subjects. If you reduce this, this is 0.642. For me, leave it like this, because I can see your thinking here. I can see exactly where you focused. So let's do another problem like this from the book. I'm actually going to change this because let's talk about COVID. We might as well. People are being tested. So we have the first row is you have COVID. The second row, you don't have COVID. And then we have our test results. So let's look at a false positive. So let's see, probability of selecting a subject with a positive test result, given that the subject does not have COVID. So no COVID, that's my given, that's this row. So the positive test result is 2 out of, well, we have to add those, 1155. That's a pretty small probability. So it's problematic for those that get the false positive because they may not be allowed to go to work, not allowed to be around family members, even though they don't have COVID. Now let's look at the false negative. Oh, kind of scratch these out. Probability of selecting a subject with a negative test result, given that the subject has COVID. That's this row. So now the probability of negative result would be 10 over 345. I'll actually do the decimal. 0.029. Well, what does the false negative do? With a false positive, the subject couldn't be around the family, couldn't go to work. A false negative, well, That's saying that, hey, I don't have COVID. When I do, think of those consequences: going to work, being around family. And that's about 3%. That could be significant. You know, somebody works at something like a grocery store, infecting a lot of their colleagues. That 3% can grow quickly, very fast. Let's just look at the last one here. The predictive value, that's find the probability that the subject has COVID, given that the test yields a positive result. So here's our positive result. We want the predictive value. Is it doing a job of finding people with positive? Well, that probability is 335 divided by 337, the total in that column. 0.994. Seems like it's pretty effective. But again, pretty effective, but still 3% false negative. That's kind of scary. But that's how we're going to do these conditional probability problems, using a table and doing it intuitively, where the given selects a column or a row for us. Just to finish this, just read this. I don't know what that symbol is. Basically, it says, be careful. Don't think that, remember, this is probability of B given that A occurs is the same as probability of A given B occurs. And here's an example. Are these both always true? Well, it is dark outdoors doesn't necessarily mean that it is midnight, because it's dark at 8 o'clock. And also, is it midnight? Does that mean it's always dark outdoors? Well, think of Alaska, midnight sun, where it is light at midnight, so that's not always true. That's just the confusion of the inverse, assuming that one implies that the other one is always true, going both ways. And that's this section.